our chart, what I have shown, a partial chart, you will be getting the full chart in the literature. Then the ratio is 1, 2, 3, 4, 1, 2, 3, and 2, 1. That depends on how do you distribute the two nucleus spin, up, down, mixed, and all sort of things. Okay, and then this 4 hydrogen, that also we know that how it would be splitted with the I equal to half. We know that 1, 4, 6, 4, 1. That means each line would be splitted into 5. So 5 lines would be splitted into 5 into 5, 25, which is fine, which is matching quite well. Now, if you look at the intensity, there is a beautiful pattern that it grows, and then it starts decreasing. And it is why? Because of the fact, this is the distribution for the proton. You need to multiply this into this, 2 into this, 3 into this. So you will be reaching maximum 18 here, 12, here 6, and that is the 18 one. After that, again it will be decreased to 12 and then to 6, and that is, I'm talking about the maximum one, and that is why it is happening like this. And that's why EPR looks very symmetric. If ideally it is correct, it looks very symmetric and rather beautiful also. Okay, so this is how one could get some perception how the lines appear and how the intensity distribution takes place. But it is good when easily understandable if your molecule is the smaller one, not the larger one. Now, another example, again, this you will see that both the things are here. I should have shown the colored and the black picture together, but anyway, it doesn't matter. You see, experimental and simulated one, it's been plotted for this particular molecule. Now, if you look at, there is a website, it's called the EG Spin, which is available in the public domain. So those who are interested, they can do the simulation by the dotted line is the simulation one. And if you you have to inject the data. If you inject the data appropriately, your simulation would be exceptionally good and almost 1:1 correspondences. If you look at the simulated and experimental one, they are moving exactly parallelly. But if your simulation is not good, that means you cannot manage to do the simulation properly, then it won't match. And if it doesn't match, then after simulation, why you are doing the simulation? You are trying to extract the necessary parameters like G parameters, like A parameters, and so on and so forth. Now, from this spectrum is very difficult. But what you can do, once you have the simulated one, then computer will tell you what is the A parameter, what is the G parameter, what is the splitting parameter, etc., etc. And you have a higher degree of reliability. If they don't synchronize on top of each other, then whatever parameters you will be getting through computational processes, your reliability factor won't be very high. So you need to have 1:1 overlapping. And if you have that kind of spectrum, then you can think about any data you are getting out of your computational process, which is acceptable. People would accept you with a proper reliability factor. Okay. Now, if you take this molecule, it's a very interesting molecule in the sense that you have many options in hand. So you have got a spectrum like around 27, 28 peaks, if I am not wrong. You can count it 1, 2, 3, 4, 5, 6, 7. This way I have counted it. You will get around 27 to 28 peaks. Now, how to interpret this thing? Now, if you consider all the nitrogens are equivalent, then you should expect 9 lines, right? 2 into 4 into 1 plus 1, all N14. Na? So 9 lines. But you are getting 28. So certainly all the nitrogens are not equivalent. Okay. And if you have the crystal structure of this molecule, you could see that nitrogens are not equivalent. Okay. But they would interact with all nitrogen having I equal to 1. They would interact with this unpaired electron. And that would lead to have your super hyperfine splitting and hyperfine splitting both together. Okay, so if you consider this nitrogen, then 3 lines, and this is directly bonded the second nitrogen would also participate into interactions. Then you will have 3 into 3, 9 lines. But you are getting 27 around lines. That means one more nitrogen is also involved. So this nitrogen must be involved into the process. So 3 into 3 into 3, that means 27 lines you are getting. You are not getting the interactions of this electron with this nitrogen, the fourth nitrogen. Well, how do you interpret it? That is the biggest concern. Looking at this molecule, I don't know how to put it this way. One is ortho, other is meta, other is your para position, other nitrogen. So your experimental result at the X band condition, I have to be very, very clear. At the X band condition, it suggests out of 4 nitrogens, 3 nitrogens have been participating in the MS and MI interaction. Fourth one is not. Now, unfortunately for this molecule, I do not have any data of Q band. Literature, it is not available. Nobody explored that thing so far. Q band and W band spectrum. Now, what will happen in the Q band and W band? Unless we do so, we cannot rule out any remote possibility of the interaction of electron spin with that fourth nitrogen. But as I said, so always once you do the EPR spectrum, EPR experiment like NMR, you have to mention that what machine you have used, so that you have made the things very clear in front of the audience or the readers that this is the condition, this is the results. So if you change the condition, results might vary, and then you have to interpret in a different way. So this is under limited circumstances, this is the best description one could put up, and everybody would accept your argument. Okay, scientific argument I'm talking about. So, but on the other hand, if you move into this molecule, you will see this is the direct, so there is no question of missing. So you will be getting doublet, and then this will be not direct because oxygen has no spin, but one bond gap. So this will be also participating. So you will be getting 2 lines. So total 4 lines will be getting as per the splitting pattern. But this carboxylate, your hydrogen, somehow it is not been participating, as because of the fact one could argue that here it is a direct oxygen bond and that links to your hydrogen, but here distance is longer because it links to carbon, and that carbon is linked to oxygen, and oxygen again linked to hydrogen. So it's a 3 double bond, 2 bond distance is there instead of 1 bond over here. So that's why only this part is interacting, this part, not this part, and you are getting two doublets. Okay, now once you get the 2 doublets, then naturally you will be getting 2 A value. Already I said what is the A value when the lines are getting splitted. Then the difference between the 2 lines, okay, in terms of the magnetic field, that means Gauss, that difference would be considered as your A value. But here though you are getting 4 lines, but essentially you are getting initially 2 lines, and each line is being splitted further into another 2 lines. So that means that one gap is the middle of this one to middle of this one. That means 1.71